database using SQL query and SQL commands. SQL commands was which part of the SQL? DDL or data definition language. Now today we will move on to see what is the rest of the SQL, specifically the part of the language to work with queries and similar stuff. Before getting into the queries, we need to see what is relational algebra, because relational algebra is the basics of the query language, is a SQL query language, and so we will use this. So today we will start with the part that we use to extract information. Before getting into SQL, we will review relational algebra. How many people know anything about relational algebra? Oh, come on, you had this undergraduate database course, right? You know. You don't know anything about relational algebra? Okay. So, basically, what is an algebra? Linear algebra, for example. What is an algebra? In general.
Transforming some expression to another expression.
You're getting close.
Finding an unknown value.
Not in general. Like linear algebra, like process algebra.
Solving expression.
Solving expression. So, what is a language?
Means of conveying meaning.
They mean that you are conveying some meaning. Okay. So every algebra has a language. Okay. In the language, you define the elements of the algebra, what you can have as operands and also operators. And algebra is usually algebra is an equational logic that have operands and operators. Okay, what is an equational logic? Equational logic is any logic that is helping you to prove or infer new information using equational operators. Okay, for example, in the numerical algebra, you in one side of the equation you have some numbers and some operators, and using some rules you get to the other side of the equation with new numbers or new expressions. Okay, the left side is an expression of the numbers and operators, and the other side is expression of again numbers and operators, but probably simpler or more complicated. So basically, relational query languages are using relational algebra. They are based on relational algebra. Basically, relational query languages are languages for describing queries in relational algebra. So these languages are usually declarative languages. Do you know what's the declarative language and what is an imperative language? Have you had these principles of programming languages in your undergraduate? You have these principles of programming languages, right? So you know that what's the difference between declarative programming languages and imperative programming languages? Any guess? A declarative programming language is a programming language in which the developers and programmers are not concerned with how the results should be computed. They are concerned to express what they wanted to run the system. For example, a SQL query is a declarative program, is a declarative language. So in the SQL query, you don't know how, probably you know how the query is processed and how the answer is extracted, but your concern is writing an appropriate expression to receive what you are intended to get, okay? But in imperative languages like Java or C++, you are supposed to tell to the computer through the language how this process should be accomplished, okay? For example, you start with a variable, you assign some value to that variable, you start a loop, you have this control of the flow of the program. But in declarative languages, you are not concerned with the flow of the program. You are concerned with the results, and you are concerned to express what you wanted as a correct query language or as a correct expression. Examples of declarative languages. SQL. The other example? What? What was that?
PLS.
Okay, PLSI? Yes, okay. Yeah. The other examples? Prolog. Prolog is a declarative language. So in Prolog you specify the rules. The rules are not concerned how you get the answer, but you are concerned with how to find correct rules to express what you intended. Okay? So Prolog in different shapes, like for example, object-oriented Prolog. Object-oriented Prolog is also again a declarative language. You are concerned to decide how the data should be structured, but you are not deciding how this data is processed. Imperative languages examples?
Java,
C++,
C++,
C++, like for example Python, PHP, all the scripted languages. So do you know what's the difference between scripting languages and other types of languages? Non-scripting languages are compiled and they have to be translated to a machine or some intermediate languages, like for example bytecode. But imperative languages are not compiled. They have an interpreter that is receiving the expressions and interpreting based on the expression. So relational algebra is an intermediate language used within the DBMS to express the query expressions, or transforming or representing the query submitted by the developers and users. So relational algebra has some, although it's an algebra, it has some procedural semantics, and it shows how this query should be processed. But SQL query by itself doesn't have any procedure or semantic. So, as I mentioned, algebra is a language based on operators and domain values or operands. Operators receiving operands are mapping one expression to another type of expression from one domain to the other domain values. So operators are basically creating new values in a new domain. So when okay, so what is the relational algebra? Algebra. I defined algebra.
Relation between expression.
In the expression, the operands are some operands, but with some semantic, but the operators. But operands are relations. Okay, those relations we studied in the previous sessions. We refer to expression as a query and every query produce a query result. Okay, so for the relational, just a brief review. For the relational algebra, the domain of the operands are sets of relations, and we have some basic operators like select, project, union, set difference, Cartesian product, and also these are basic operators, and the rest is derived operators. What is the difference between derived operators and basic operators?
Basic operators are the system provided operators. I mean,
In terms of algebra, don't think about the system operations.
the basic operators.
Direct operators to the
Yes,
and derived from
they cannot be derived. Okay, but the derived operators are
Derived
those that can be expressed again in terms of basic operators. But we are using it in order to increase the abstraction. Okay. Okay, so this relation is basically expressing an algorithm, but we don't need to. We are not concerned with the exact algorithm. So basically, this is the story going from one SQL query to executable code. Basically, when you submit a query, there will be a parser. Okay, the parser will parse your query and understand what kind of tokens it has, and also it has a syntax analyzer. Have you had compiler course in undergrad? Do you know how compilers are working? Okay. Are you kidding me or? I mean,
They construct trees from the expressions and then they'll evaluate.
there are several steps. They have to syntactic. First, they have a tokenizer. They extract tokens from the program. For example, in the first round, if you give a Java program to a compiler, it's a Java compiler. It recognizes all the keywords, all the variables, all the expressions, all the operators from the program, and then that the set of tokens will be fed to a syntax analyzer. The syntax analyzer checks the syntax of the program, okay? And the syntax analyzer is also, the result of the syntax analyzer is together with a semantic analyzer and code generator generates the target code, okay? So the parser here is a mixture of tokenizer and syntax analyzer. Basically, the query will be parsed, and then the query, after query is parsed, it will be query optimizer's task to first create relational algebra from those query, or interpret it in terms of relational algebra, and then provide us with the efficient query execution plan. What is a query execution plan? It's instructs the machine or the DBMS how to, which steps it should take to collect the results from the different relations and tables. And finally, this query execution plan is translated to executable code for DBMSs. Okay, the first operator of relational algebra is select operator. It's a very important operator. Select operator basically produces a new table containing all of the columns from the original table, but some of the rows are filtered. Based on what? Based on the condition. So select operator is selecting those rows that are satisfying that condition. Okay, for example here, if we put the condition hobby is equal to stamps, and this is the person, this expression, this relational algebra is returning this relation, is equal to this relation. Why? This was the person relationship. So in this relationship there are two rows that hobby is equal to stamps. So what this operator does is basically filters these two columns, these two rows to the new table with the same domain. So the select condition can have inequality operators, inequality operators, and also it can use those operators can be used on between two attributes or an attribute and constant. For example, here I've used the condition. The left side of the condition was an operator. The left side of the condition was an attribute, and the right side was condition the constant. But you can have two attributes at the order. So, and these conditions can be can be extended with logical operators. These are examples of select operator. Okay, the other important operator is project operator. Project operator is when you apply project operator with some name of the domains, some column names. What it does is basically it creates a new table, or it extracts the table with the same number of rows but with different number of columns. Is that true that it has always the same number of rows?
It eliminates the duplicates.
Yes. In relational algebra we don't have duplicates, okay? If you remove some of the columns, and based on that removing, the results have some duplicates in the table, the result table has some duplicates, then those duplicates will be removed. Therefore, this operator also may create some table or relation with less number of rows than the original one. Here, for example, we had this person table, person relationship, and we projected name and hobby from that. Then the name and hobby column was extracted. So, and okay, so now it's an algebra. So you can use these operators on top of each other. You can use these operators on each relational algebra expression and get a new relation, right? For example, here, first we use selection operator on person table based on to filter all of the rows that have hobby equal to stamps or hobby equal to coins. Okay, then based on what we have in the inside of the two parentheses, we will select these three rows. Okay, then after that we will project the two columns, ID and name, and based on that the result will be this one. Why just two number of rows? The result of the
Eliminated the duplicates.
duplicate. Okay, now set operations. So relations are basically sets. Sets of tuples, right? So if it is a set, then we can use set operators as a part of relational algebra. Therefore, intersection, union, and also set difference operators can be also used in this algebra. The result of using set operators are usually a set with the same domain, the same number of columns, but with the number of tuples equal or less than the number of tuples, the total number of tuples of those sets or inputs. One more thing is that scope of set operations are limited into union compatible relations. What does it mean?
They should be of same entities,
Same
same columns.
columns, exactly the same domain. So one more question. This time of, do you want to have a competition between this part of the class and this part of the class, the west side and the right, the east side, and then see, because I see that you're not, this part is not contributing, so. Okay, two relations are union compatible if both have same number of columns, name of attributes are same in both of the tables and relationships, and attributes with the same name in both relationships have the same domain. So this should be exactly so if we define the domain of a table, an attribute in a table among these three values, like and we have this domain. Okay, so these two domains are different. Okay, although they both of them are stored as with data type of string, but if you in one table you have this one attribute with the domain of everything. For example, what was said the last time, and the other table is the same attribute what was said the last time, but one is using this domain and one is using this domain. You cannot have reset operators on those variables and relations. Here is a couple of examples. For example, these two tables cannot be, they are not union compatible, but table person and professor can, they are also okay, so these two relations are union compatible. Why? There's two columns. This relationship has one column which is name with the same data structure, and this also in the same column. So the next important relationship is Cartesian product. Cartesian products are a type of product or operation you can define on sets or sets of tuples. Okay, so basically what it does is it for each tuple x from R, if we have R multiplied to S, for each tuple from R, X, and for each tuple Y from S, it creates a new tuple X and Y, and it puts it in the result. So this operator does not require those two relationships should be set compatible. Although Cartesian product is a set operation, it is not requiring those two sets to be union compatible. So, but the most important part is this. This Cartesian product for all the DBMS system is a very, very heavy computation, and it's very expensive to compute. Why? What's the order of the computation of this?
N-cube.
N-cube. Why is N-cube?
Maximum matrix.
N-cube or N square?
N-square.
Size matters, and for each relationship you take all of the rows, and for the other side, for each of those rows you have to repeat in order to create new tuples. Have you ever used this? Do you have any experience with Cartesian product in the DPMS systems? We will get to join, but join is very popular in DBMS systems, right? So when you are writing join queries, sometimes if you forget some equality or the condition of the join, then we will Cartesian product. It happened to me several times. You write a query, you miss some part of it, and when the user is submitting the query, or when you embed the query, for example, in Java program, and the Java program is executed, then the system will be going to sleeping. Not sleeping, the system is not responding, and it's getting involved in this heavy computation in which you are computing a very, very big table. So, renaming. Why do you mean renaming?
For columns with the same attributes when they are joining, they need to be named.
Right. So with renaming, you rename the columns, and then based on that, with this renaming, you will have a lot of options. For example, if two different relationships have the same number of columns, each column in one relationship is from a data type similar to its correspondence in the other table, but the names are different. These two relations are not set compatible. They are not union compatible. But you can rename the columns in order to make them union compatible. Or you'll see in the joins, in natural join, how this renaming is working. Basically, the rename operation is working like that. If you have an expression of relational algebra over here, and you put a square braces over here, then the first column of the result will be renamed to A1, the second one A2, so on to AN. So this is a kind of naming of an expression of relational algebra. Here, for example, here we can, or in this part, we have one expression. We are projecting student ID and course code from transcriptive relationship, and we are using, we are projecting prof ID and course code from teaching relationship, and then we multiply it while we are renaming these two columns. So if we don't rename it, what will happen? What will happen if we don't rename these two columns to different names?
In the resulting table, you don't know what the column name to put.
Exactly. In the resulting table, there will be an ambiguity. You don't know which column is corresponding to which table. Okay, so we have to, for example, in here, we have to rename those columns in order to resolve this ambiguity. So the first derive operation is join. Okay, we start with, now we move on to derived operations. Join is called, basically the basic join is called general join or theta join, which is shown in this format. You can see over here up there. For example, basically what does it mean?
Question once again.
So what? And the result will be the table. The result will be.
It will check the condition and whatever tuples accepted condition, it displays the condition also.
Exactly. This is a kind of refinement of. This is a kind of refinement of Cartesian product. Basically, you define a join, natural join between two relationship. When you are doing this, you define a join condition over here, like using two columns, one AI and the other column BI. AI from relation R, S from relation BI from relation S, and these two attributes are compared with using one of these comparison operators, and whenever the result, the comparison is satisfying the condition, then that column, that row will be included in the result. So this natural join can be expressed in terms of what? The Cartesian product and select. So, but and the join condition here is a bit different. The join condition, in the join condition, we can have renaming of attributes. For example, so why do we need to rename the attributes? Exactly, we are resolving this ambiguity. If we don't rename them, then in the expression we don't know which column corresponds to the other part. There is a common way of renaming columns. Basically, what you are doing in school query, I'm sure that you have used this convention that you are mentioning the name of the table, you put the dot and the attribute name, and for this part is also similar, and you in this way, with this convention, you distinguish between two attributes in the joint condition. Okay. Here, for example, okay. So we want to write it. We have these two relationships. One relationship is showing the employee with this domain. The first column is name, the second column is the personal ID. The third column is showing the manager, the ID of the manager of a person, and the last one is representing the salary. The second table is just is just showing the managers and how and what they are receiving. So these two tables can have overlap. So assume that these two tables can have overlap. Now we want to compute a relationship where the names of all of the employees that are getting more than their boss is shown. Okay. So what we are doing is basically, first of all, we want to output the name of the employee. Okay. The join should be between two tables, employee and manager. The condition is that the manager of the person, okay, the manager of the person should be equal to the ID of from the manager table, and the salary from the manager table should be less than the salary from employee. But if we don't use that convention, this will be ambitious, okay, and ambiguous. Why? Because we don't know which ID it is. ID from which table, or which salary it is. Okay, so we are using this convention to show which attribute we are pointing at. Okay, so what is assume that compute or write an expression right now, in a couple of minutes, to show the name of the managers that are getting money or salary less than their employees. And the salary is higher than 120K per year, 120K. Okay, reflect or compute a relationship in which there is just the name of the managers who are getting less than their employees, okay, who has an employee who is getting more than that manager, and also the salary of the manager is more than 120K. Expression should be like this. First of all, we just need to have the name of the employee, managers. Okay. Then on the result, we put this projection to make sure that the result will have just to make the result to have just the name of the managers. Then we had this condition that the name of the salary of the manager should be more than 120K. Then from the result of this table, we have to filter or select based on this condition. The salary of the manager should be more than this amount of money. And also the rest of the query will be similar. Why? We have this condition, we had this expression that the manager there should be some employee that gets more than what the manager gets. Okay. Now let's. The most famous form of the join is the equi-join, where basically what we are doing is we are the join condition is just equalities, okay? And we can either select the columns from two tables, or we can, if the name of the attributes are similar, then we don't need to specify the condition. For example, here when we are doing a equi-join on the student and transcript, we know that the student ID here is a foreign key to ID in the student table, okay? So when we want to join, we know that although the name of this attribute is different from that attribute, but these two attributes have same meaning, then when we do equi-join, basically we put this condition to make sure that ID is equal to the student ID, and therefore we can see who is taking which course. Okay, suppose that this transcript table shows which course is taken by each student and what is the grade. So if we want to get the result as name and course code of each person, we can get the name of the course code of each person based on the relationship. And another condition is that the grade should be A in the transcript. Okay, so natural join. What is natural join?
Equi-join will be performed on with same columns.
It's the same column with same name. In this case, call it, it's kind of renaming equi-join. We rename it natural join. It's a kind of calling conventions and terminology. So the natural join, for example, the natural join of these two tables, how many columns it will have? How many columns the natural join of these two tables will have?
2 columns.
What?
7.
Seven or five?
2.
Why? Because these two columns are the same name, the same value. Therefore, you don't need to repeat them. Okay, so this is how we can implement natural join with other operators. This is how natural join is derived from other list of operators. And you see that since the attribute names are similar, then the columns for the attributes are overlapping. Here is another example of natural join. Basically, so we are renaming the transcript table with the same student. We rename the transcript table and use it as another operator to see which one of the students has taken 2 courses, at least 2 different courses. Is there anyone can explain how this expression works? First of all, we say that this all IDs, okay? Then the resulting expression should just project IDs, the student IDs, okay? So this is clear. have this transcript table, okay, in order to catch a person with two different courses, we repeat this transcript on natural join, while we rename the transcript. The name of the column, student ID, is still the same, so the result will have a table with the same number of columns, but if the student has two courses, has to take in two different courses, then the natural join will have a row where the course code 1, 2 from this part of the relation, this side of the operator, will be different from course code from this side of the operator.
But that is the same table, right?
No.
Same transcript. Same table, right?
Okay, so we are renaming transcripts. Yeah. The same relationship, but we rename the columns.
Yeah, but the entries will be same. So when you are not
How many columns this relationship will have? Just this part.
Four columns.
Are you sure? Or completely sure? It has one course code, SEM, grade for course code 2, SEM 2, course code
that's all.
grade 2. So this is it. We are renaming it, okay? From the point of view,
But the entries inside will be same.
interest will be same. No, doesn't matter. But for
But-
each
but-
student, for each student ID, when the student ID is similar, if there are two different courses, they will be productive. There will be.
But when you are duplicating the same courses will be there and you are projecting and you are selecting when you are selecting which are not equal, there will be zero entries, right?
No. Why is it zero entries?
Because you are just duplicating the table.
So I duplicate the table. When I duplicate the tables, this natural join works. I rename, okay? When I rename the course code, okay, these two columns will be two different columns now.
But
Assume that, okay,
the subjects will be the same subjects.
the subject is not the same. The students are the same.
Okay.
Okay, the students are the same. Okay, for example, well, I cannot finish this lecture. But we will continue on Thursday. Suppose that you have a transcript table with the student ID 111. Course code, semester, and grade. Okay, 111 took CSE, CS 551 in fall 2016, and he got B. The student one took CS 514 in fall 16, he got A. The student 112 took MT 555 in fall 16, got B. Okay? So what we are doing here is the inner part of this expression, Okay? What it does is basically it copy this table to another table, but rename the columns. The column name will be ID, course code 2, semester, and grade. So the data will be the same.
I got it, Professor.
You got it? Okay, so let's see. Other people, you got how it works? Okay. Fall 16, he got A, he got B. 111, CS 514, fall 16, you got A, and 112 in MT 555. She got it. Okay, so first of all, tell me what should be the result of this query. This all IDs of students who took at least 2 different courses. What is the result of this? Without checking this expression, given the fact that this is the transcript table. One. This guy, he took 2 courses, 2 different courses. Okay? Okay, now what we want to do is basically I want to show you what is the result of this Cartesian for this natural join, the inner side. For a second I will bring it. You have a transcript table, natural join with the transcript table, why 3 of the columns are renamed. Can we start going on now? Okay. So the result will be what? What will be the result? The result of this one multiplied to this one, so the natural join of these 2 tables will be okay, so the result will be a column with ID because it's just one ID column because it's natural join. But course code SEM-G for semester grade. Sorry, this one is semester 2. This one, and also course code 2. Semester 2 and grade 2. Okay, so the result will be 111, the same CS 551. Semester fall 16, he got B, CS 551. Semester fall 16, he got B. Again, this the same person, 111, semester, so for course CS 554, so 551, this is 551. In fall 16, he got B, and in CS 540, in fall 16, he got A. The same person, in course CS 540, in fall 16, he got A. In CS 551, in fall 16, he got B. The same person in CS 514, in fall 16, he got A. CS 514 again, 40 again, in fall 16, he got A. And the last one is the guy 112, he has taken this course in fall 16 again, he got B. And this is also MT 555, in fall 16, he got B. Okay, so from this is the result of the natural join of these 2 tables. Okay, in the result of this natural table, if you want to select rows that are the course code 1 and course code 2 are different, which rows should be selected?
First, second.
Second one and the third one, right? When the course code 1 is CS551, the course code 2 is CS540. And the third one, when the course code 1 is CS540 and the course code 2 is CS551. Okay, these two courses will be selected. Now, the result will be here, okay? Sorry, I just... These two rows are selected. Okay, so now if you want to project just a student ID, how many rows should be? Why? One, because it's duplicated. Okay, so we will continue on SQL next week. And also please write. Okay.